So if you got no question, now let me just go over this last part, which is how we can treat the sharpness issue in the VAE. And I put this one in particular here because most of things that nowadays people use in practice are usually working with this vector quantized VAE. You might have heard of it. And then you need to know a tiny bit of more things to just get exactly what it's doing. So when this issue of sharpness happened, so people started to say that, okay, what if we can somehow get back to the original idea of generating by autoencoders? And what was the original idea of generating by autoencoder? We said that we train one encoder-decoder pair, which is able to perfectly reconstruct X, right? So every single X that I send, I am going to compute the loss between encoded and the decoded version in this form, right? The X itself, what is going inside the encoder, is supposed to be exactly like what is coming at the end of the day out of the decoder, right? And then we put here no Gaussian sampler, nothing, right? So this E and G, both of them are just neural networks, which takes some image as the input and give you some tensor at the output, right? So people started to say, okay, what if we get back to this old idea that we had before VAE? And the main thing is that we just train this guy. Once that we have trained this guy, we need to just sample. We need to somehow understand how we can sample from the latent space, right? What if we go ahead and do or develop some framework which helps us understand the distribution of the latent, right? This is why I put a question mark here. We don't know exactly how we can do it right now. But what if I can do it, right? If I can do it, then the problem is solved, right? So I'm going to go and sample from that distribution, pass it through the decoder, I get my sample. No Gaussian noise, no sampling anymore, no blurriness, right? Blurriness, right? Is it the right word? Blurriness. So there is no issue with the sharpness, right? So this is the idea that they had, and the question was how we can learn this distribution. Okay. One thing that you should pay attention here is that people started to conjecture that this is going to resolve the issue because there is essentially no Gaussian thing here. And what they said like if we are 100% sure that this particular point in the latent space is a valid latent from the data, right? So it's really the latent representation of one cat image. If I can make sure about that, then of course I can take this latent, pass it through the decoder, and as long as my decoder is perfectly trained, it can exactly recover the cat image, right? So there is nothing added to it to just make that kind of noise into the image, right? So this was the main idea that they had. Maybe we can get back to the original idea. And given that we have developed so much frameworks in generative models, maybe we can do it again or look at this problem once again. And then we can use those frameworks to resolve this issue, finding out what is the prior distribution of the latent. Okay? So that was the idea. And the key challenge, as I said before, was that this prior distribution is unknown to us, right? So we need to learn it. In the VAE, we have this property that we use variational inference to impose it to be Gaussian, right? Look like a Gaussian. Since we can force it to be Gaussian, then we know it, we can sample from it. Now, we're not doing variational inference anymore, right? So we cannot do it, right? So this was the issue. And in practice, the latent representation could be as weird, or the distribution could be as weird as this guy, right? Like you pass as much as data you want, you do not see any kind of well-defined distribution. You start to see like latent representation are expanding in different directions, right? Now, based on this one, you cannot say where the valid data point is, right? For example, if you just take one sample from here, well, this is somewhere where the frequency is high. This is probably very valid, right? But if I take something from here, even though it is very close to these ones, which are very high frequently happening, nothing is happening here, at least in the samples that I have tried, right? So there is no well-defined distribution that I go, okay, this is a circle, and I just sample from the circle, right? This was the whole magic of variational inference, right? It was making it to look like a Gaussian, right? Whereas in practice, like if I don't control anything, it's going to look weirdly, right? Now, people started to think out of the box. One of the things is that given what we had before in chapter 3, we do know that we can learn a distribution, right? If I have data samples, we can try to learn that distribution, right? How can I do it in this particular setting that I have? Okay, let's do it together. Say I want to just make an autoencoder which is learning a kind of general latent. How can I do it? I have my encoder, I have my decoder. I don't care at all about the distribution of the latent. I'm going to train it to just do perfect reconstruction. Every single sample going inside the encoder and coming out of the decoder should be the same, right? So this is the classic autoencoder. You can simply train it. Yeah? Once you train it, you are over. Now you have your encoder, right? Now that you have your encoder, you're going to get every single training sample that you had, you pass it through the encoder. What's going to happen? You're going to get a bunch of latent samples, right? These are all the samples in the latent space, correct? Then you're going to get those latent samples. You just collect them in one set. You're going to call it latent data set. This is the transformed, the encoded version of your own data set. And then you start training one explicit model to learn what is the distribution of this latent, right? If you do that, then you know that distribution by this model, say P5, and then you sample from P5, you pass it through a decoder, you get your image, right? Does it make sense? Does it sound like something possible? I mean, it makes sense based on what we have learned up to now, right? So the decoder is able to transfer latent to the image, right? And if your model P5 is trained well enough, like what we did in chapter 3, then it is able to learn the distribution or capture the distribution of the latent, right? Now, when you sample from this model, you're going to get a valid latent. That valid latent goes through a decoder. Then you're going to get a valid image, right? So theoretically, it makes sense, right? But when you want to do it in practice, you might have a bit of trouble. So what is the key trouble here? In this formulation that I gave you here, this latent representation, what is it? It's a vector in a, say, m-dimensional space, right? Is it continuous or discrete? It's a continuous thing in general, right? So your encoder is going to compute one vector. This is what we did it in VAE as well, right? All of those latent samples are continuously distributed in this space, right? If I think of my latent to be two-dimensional, it could be any point in R squared, right? It could be any point. But now, if you have a data set of a bunch of real valued samples in a very high dimensional space, then is it easy for you to train a model for its distribution? We have seen it in chapter 3. It was quite hard, right? If you want to do it, probably you need to go for something like energy-based model, right? And that guy is quite hard to sample, to design, right? To train, sample, and other things. What is easier for us to train? Sorry? Quantized version. If my latent is discrete, I can do it easily, right? Why I can do it easily? Because when it's discrete, it means like every single entry inside my latent has a few cases, right? And then the distribution at the end of the day is described by a softmax, right? So I can simply use what we did in chapter 3. Basically, I can use autoregressive modeling to just learn, step by step the distribution of every single entry, right? So that it was the main change that they did. So they say, okay, maybe we can, instead of considering a continuous latent, maybe we can focus on a discrete latent. And if we enforce the latent to be discrete, then this latent is going to belong to a limited set of numbers, right? Now I can describe any distribution on that by a softmax, If the latent is very long vector, then I can just use autoregressive modeling, right? I just find out what is the distribution of the first entry, then condition to that, the second one, condition to these two, the third one, and so on till the last one, right? So as long as you make it quantized, you make it discrete, this is going to be not that challenging, right? And this was the motivation that people tried to migrate into discrete latent space. So what they did, essentially, they said, OK, let's assume that we have a kind of code book. So what is code book? Essentially, this is the embedding that we used to do in language models, right? So it would say that any latent that I want to represent is going to be one of the k possible tokens, 1 to k. And every token, I show it by one vector, c1 to ck. These are what we call it code words, right? And this set of all of the code words is the code book, right? Now, any latent that you have is one of those, I mean, any entry of your latent, or any, say, for the moment, any latent that you have is one of those few code books, right? In other words, any input image that you have, it's going to be encoded into one of the possible tokens, right? And then when the number of tokens is finite, you can learn the distribution, right? This was the main idea. So this is what we call it the code book. And then in this case, since the space of possible cases for your latent is finite, then you can efficiently train an architecture or a distribution model which is capturing the distribution of that latent variable. Everybody's clear? So I mean, there are a bunch of them out there, but the most sophisticated one is the vector quantized variational autoencoder. And it was specifically designed for training a kind of visual model, like working with images, tensors. So how does it work? I mean, basically, first of all, it's very good for visual and audio data. Nowadays, most of the things you see working with variational autoencoders, they're usually, I mean, when it's visual, they're using this vector quantized version. Yeah? And one thing that, I mean, first of all, they quantize it into exactly a code book. I'm going to explain the architecture in details right now. And one thing is that those entries, those code words inside the code book, they actually leave them also learnable. Like C1 to CK, they don't say that they are strictly these points, right? Exactly like embedding in the language models. They just leave them as free parameters, and then they train them by backpropagation. Okay? And one thing that you should pay attention here, I hope that this is clear for you, this is technically not variational autoencoder, right? Because we're not using variational inference anymore. Even though they call it VQ-VAE, variational autoencoder, it's not variational autoencoder. It's the classic autoencoder plus learning the prior distribution, right, of the latent. But since everything is VAE, people call it VAE as well, right? So it's not really using variational inference. There is no ELBO anymore. KL divergence gone, right? All of the nightmare gone, right? But people still call it variational autoencoder. So it would be better if you call it like VQ-GAE, generative autoencoder, right? But anyways, this is the terminology nowadays. So this is the architecture. I don't want to break it down into details for you anymore because I think you have enough of that. But the main idea here is that you get your input, and you usually work with images or tensors, right? And then you have this big tensor as the input. You are first going to do encoding, right? When you do encoding, the output of the encoder is again a tensor, right? Like it has so many channels, correct? And now you look at all of these channels, and then what you do, you are going to look at every, I mean, if you think of an image, say RGB image, every single pixel is not a number, right? It's a vector of size 3. Because RGB, all the 3 pixels, right? When you do encoding, the number of channels is going to be larger, right? So you might have, I don't know, 20 channels. And then you have an explicit size. Now, you look at every single of these huge pixels as one single component, okay? So when you do the encoding, you're going to end up with this vector u. Maybe I can again, I know this is going to make, we are already very, I mean, is it okay that I finish this part, or should I just skip it because it's just 2 minutes left? Is it okay to, that I finish it, or? I know I am making you super tired, but I promise next session is going to be short, okay? Okay. Yeah. Okay. So, yeah, here. So every single of these guys, as you see, this is one entry, right? And now you have lots of them. So let's say we have m different of them. When you do the encoding, this guy, this vector ui, every single of them, this is going to be real valued, right? And then you want to quantize it. What you're going to do, you're going to put one code book, right? And this code book is going to have k different cases. Then you look at every single entry inside your computation, that every single of these u vectors, and you see which of those code words is close to this one, the closest guy. The code word which is closest to your u, right? And then you're going to take that code word as the code word representing your latent, right? For instance, say I take one u, I get ui, and I see that c1, the first code word, is the closest one. So I'm going to put 1 here, right, in this table. And then when I want to represent my latent is going to look like this one. And that particular, going deep in channel, that vector is c1, right? Same thing here. Say it's close to c8. I'm going to put c8 here, and so on, right? So you get your real valued latent, first u, and then you just find the code words which are close to every single component, and that one is the quantized version, okay? And now the quantized version is discrete. You're going to pass it through the decoder to recover. Everybody's clear? So the whole idea is that you do just